In this recording, we look at a second example of inverse functions. And for a function y equals f of x, in order for it to be a function, for each value of x, there must just be one unique value of y. And when a function y equals f of x is strictly increasing, like this for instance, or strictly decreasing, let's say like that, on its whole domain, then for each y value in the range, there is also a unique x value. And a function of this type is called one-to-one. And if we have a one-to-one function f of x, the reverse relation will also define a function called the inverse function f inverse x, written in this form. However, if y equals f of x is not strictly increasing or strictly decreasing on its whole domain, for instance, if we had a function like that, then to define the inverse function f inverse x, we would need to restrict the domain of f of x to an interval ab where it is strictly increasing or strictly decreasing. And one thing we can note, which can help ensure we do this in a consistent manner, is that the restricted domain of f of x, which will be the set of x values we can input into that, will be equal to the range of the inverse function. That is the set of y values that will be output by this inverse function, while the domain of the inverse function will be the range of the original function. So let's see how this works in practice in relation to an example. Let's look at obtaining an expression for the inverse of the function f of x equals x squared plus 5. So in this particular case, let's start off for convenience by writing that just as y equals x squared plus 5. So writing y for f of x. And it can help to look visually at what this function is like. And this is a quadratic function because of the x squared, so that will have a parabola for the graph. And y equals just x squared would be a parabola pointing upwards with the vertex at the origin. X squared plus 5 means it is a parabola shifted vertically upwards by 5 units, so that it will be a parabola like this with the vertex at 5 on the y-axis. So this is not strictly increasing or strictly decreasing throughout. It is actually a decreasing function for all negative values of x as we head towards 0, and then it turns around at that vertex there at x equals 0 and becomes an increasing function for positive values of x. So we need to choose one side of this to restrict our domain to when we're defining the inverse function. And when it changes at 0, it would usually be, in most cases, the most common convention to pick the positive side of that. So let's do that. Let's restrict the domain of f of x to x greater than or equal to 0 to help define f inverse x. And we'll come back to that in a minute, but first let's just do some of the algebra to find the inverse function. And one convenient way to work out the inverse function is to interchange x and y in the original expression, so that becomes x equals y squared plus 5. And then we rearrange that expression for y, which will relate to the inverse function. So just swapping the sides of that equation for convenience, y squared plus 5 equals x. So y squared equals x minus 5. And that means making y the subject, just algebraically before we think about the function, y comes out to be plus or minus the square root of x minus 5. But that is not a function, is it? Because we said for a function, each x value must have a single unique y value, and here, for most x values, there will be 2 options for y. So that is not a function. But how do we decide which branch of this is actually the inverse function that we require? And this is where the property that the restricted domain of f of x will be the range of the inverse function. That is where that comes in handy, because we restricted the domain of f of x to be x greater than or equal to 0. That means for the inverse function, the values of y taken by the inverse function must be greater than or equal to 0. Which means it must just be, the square root here will always be positive, so it must be the positive branch of this, and we would reject the negative alternative. So getting rid of the negative, we would say y, and hence the inverse function, f inverse x, is in fact just the positive form of that, or the square root of x minus 5. And sure enough, it has a range of values of y. Y for that will always be greater than or equal to 0. And let's just confirm that other characteristic we saw before, that the domain of the inverse function should be the range of the original function. So what is the domain of f inverse x? And the domain, the natural domain of this, is the set of all x for which it is defined. And the square root of a negative number does not give a real answer. So the expression under the square root sign must always be greater than or equal to 0. And for x minus 5 to be greater than or equal to 0, we must have x greater than or equal to 5. And so that's for f inverse x, whereas if we look back at f of x, which we started with x squared plus 5, you'll notice that the range of values taken by that, the minimum for f of x, was at the vertex where y was 5. So the range there was y greater than or equal to 5. So sure enough, the range of f of x was also the domain of f inverse x, in addition to the restricted domain of f of x for defining the inverse being the range of our inverse function. So it can also help finally to see this picture of the two functions on a diagram. This parabola was f of x, and then we restricted the domain of that to just this part here. And this one over here is the inverse function, the square root of x minus 5. And on this diagram, the line y equals x is also shown. That is a diagonal line. And you'll notice visually that the restricted part of the original function, over which we used it to define the inverse, and the inverse function, those are a reflection of each other about the line y equals x. So the main thing to remember here is always check whether your original function is strictly increasing or decreasing throughout, and if not, before defining the inverse function, you need to restrict the domain to where it is increasing or decreasing throughout, and then proceed as we have shown.